All right, so before we move along to transmission and distribution stuff, I want to very quickly introduce you guys to the concept of three-phase transformers. And hopefully, unsurprisingly, we can consider a three-phase transformer just three single-phase transformers where each transformer phase is responsible for transforming one phase of our three-phase systems. So we can have YY three-phase transformers, delta delta three-phase transformers, and lastly a Y to delta three-phase transformer that can be used to. So let's look very quickly at a YY transformer first. So I'm going to give myself a terminal here, and this is going to be for the A phase of my primary. So the A is for the phase, the subscript notation is for whether we're on the primary side or the secondary side. And I'm going to draw something really quickly here. So I'm effectively just going to draw one side of my transformer first. So this will be the B phase of my primary. And the C phase of the primary side of my transformer. Let me put my dot here. Now I'm going to draw my lines representing perfect coupling. And now I'm going to draw the secondary side of my three-phase transformer. Put that over. That over. Oops, sorry, I drew this one backwards. Sorry, this is getting messy. So let's put something here. So this is the A phase of my secondary, the B phase of my secondary, and down here will be the C phase of my secondary. So I effectively have two sets of Y connected coils kind of superimposed on top of each other in order to form a transformer. Our turns ratio will still be simply the ratio of N2 to N1. So if we call this our line voltage on our primary side, and I'm calling it a line voltage because it's measured between the transmission line terminals. And this will be our line voltage on the secondary side. Then we should have a relationship that, excuse me, VL2 over VL1 should be A. if I consider this current as a line current on the primary side, and this as a line current on the secondary side, then we should find that IL2 over IL1 is 1 over A. And the total complex power on the primary side has to equal to the total complex power on the secondary side. So there's our YY transformer. It behaves exactly like we should expect. The voltage on the secondary related to the voltage on the primary is just a factor of A, current on the secondary versus current on the primary, 1 over A, just like we saw with our single phase transformers, nothing weird there. Complex power in equals complex power out. Nothing remotely different about how this guy behaves. Our delta transformer is going to have a similar set of relationships. So let's go ahead and draw that one. So here's our primary A phase terminal. And something like this. Here's our primary B phase terminal. Drawing the B phase backwards. My apologies. So there's my primary side. So now I'm going to draw my secondary side. I'm going to draw my coils first and then kind of fill everything else in. So this should be A2 down here will be B2 and here will be C2. And so we've got two delta connected sets of coils kind of superimposed on top of each other to form a transformer. Once again, our turns ratio will be A is equal to N2 over N1. So if this is our primary line voltage and this is our secondary line voltage, so both times measured between the A and B phases, we have the relationship VL2 over VL1 is equal to A. This is my primary current. And this is my secondary current. Then we would have IL2 over IL1 is equal to 1 over A. And the complex power absorbed or supplied by the primary side has to equal the complex power supplied or absorbed on the secondary side. Again, the relationships for the Y-Y and the delta-delta transformers are literally the same thing. All right. It's literally the exact same equations. So now let's do the gross one. So this will be our delta to Y. And let's call this A1. This will be B1. Guy right here will be C1. And this guy right here will be the neutral conductor. So hopefully we can all see that what I've drawn to this point is a Y-connected set of coils. So I have a coil between A in neutral, B in neutral, and C in neutral. And on the other side of things, now I've got to draw a delta connected. So let's put the terminal A2 here. And so what I'm going to do is I'm going to tie this A2 terminal over to here. And I'm also going to tie this leg of this coil to that same node. For my B phase, I'm going to tie this leg of this coil to my B phase, this leg of this coil also to my B phase. So here's my B phase connection. So I now have one coil between A and B. And down here on C, I'm going to tie this leg to C and this leg to C, like so. And now that coil in the middle is connected between B and C, and the coil on the right is connected between A and C, so that I have a delta connected set of coils on the bottom. So we are going to be converting. So let's call this voltage here VL1, and this voltage here VL2. Okay. So our mathematical relationships for this one will be as follows. So VL2 over VL1 will be equal to IL1 over IL2. Let's define those currents. So this would be IL1, and this would be IL2. So the ratio of the voltages is equal to the inverse of the ratio of the currents, exactly like what we saw before. But instead of it just being related to each other by A, it'll now be A over the square root of 3 because we have a three-phase system. And this set of equations is for treating the Y as the primary and the delta as the secondary, or converting from a Y-connected set of voltages to a delta-connected set of voltages. If we want to go the other way around, it would be the exact same transformer. So I'll write it as VL2 over VL1 is IL1 over IL2 will be square root of 3 times A, and this is for us to go from delta to Y. I want to make a caveat here for the second set of equations. We are treating the delta connected set of coils as our primary and the Y connected set of coils as our secondary. So primary or secondary, that is just a nomenclature kind of thing. So in my limited experience, and Ron could probably talk more about this because he has much more practical experience with this than I do. I consider the primary side to be whichever one is connected to my voltage source, and the secondary side to be whichever one is connected to my load.
So I remember you talking about it, but I didn't remember like how important it was, like if that is.
It doesn't, so a transformer is effectively interchangeable. And so by that, I mean, let's say that we purchase online a step down transformer, which means that we would be stepping down some high voltage to a lower voltage. If we literally connected our transformer in the opposite way, we would have a step up transformer. It's literally the exact same thing. We just apply one set of voltages on the low voltage side and take the high voltage terminals to give us that. So transformer is a transformer. Like there's nothing on there that's explicitly marking primary windings or secondary windings or anything like that. It's just whichever set is on the source side, we typically refer to as the primary. Whichever set is on the secondary side, we refer to, or excuse me, whichever set is on the load side, we refer to as the secondary. But transformer is just a transformer. It's literally just coils of wire wrapped around a ferromagnetic core.
We do that in the first two recent one sessions. Using the same transformer at one time, you connect the one side to the source and step it up. The only time to flip it around, connect the other side to the source and step it down.
Yeah, I mean, it's literally the exact same piece of equipment. So pretty much, yeah. For like, if you were ever wanting to know, so how do you think voltages on transmission lines like outside are measured? Like, let's say that we wanted to measure and make sure that the voltages on the lines outside were actually 13.8 kilovolts RMS. So it is no big old multimeter at all, right? So a multimeter would not be rated to be able to do that safely. What we do is literally we attach a transformer with a known turns ratio and use that to electrically isolate our measurement system from the live wires and use the turns ratio of the transformer. So whatever we measure on the low voltage side of that transformer, multiply that by the turns ratio, and it tells us what the voltage is on the lines. So, yeah.
then when the power comes back to the transformer.
So you're missing a little something there. So a solar panel generates DC power. So your solar panel would actually have to be fed into what's called an inverter, where an inverter is a power electronics circuit that converts DC power into AC power. Then, if you're going to try to have a grid tied in system, you actually have to make sure that the frequency that you have perfectly matches the grid and all of that kind of stuff too. So that's more expensive power electronics that kind of takes care of all of the frequency matching and all of that kind of stuff as well. So there are multiple degrees of isolation in which transformers are used, by the way, to provide that electrical isolation to make things work. So, did that?
So, like, let's say you had like let's say you have your own generator set,
Mm-hmm.
and you wanted to put power back to power. Get it all set up, it is all the right, good, all the right frequency. So then, would the transformer be able to keep the power you generate and put it back into the power?
Yeah.
Yeah. The solar panel on top of it, having your own.
Yeah. But there's, I mean, it's not as simple as just connecting up a generator and calling it a damn day. Like you have to match the frequency and all that kind of stuff, because if you effectively dirty up the power that the utility is providing, they are not going to be happy. So there are power electronics things in there that are providing electrical isolation while also helping to maintain frequency matching and all of that kind of stuff, so that the power on the grid as a system is clean, and by that I mean undistorted as it can be. Because there are certain electronic devices like your televisions and things like that that contain sensitive microelectronics. And so you want, this is getting way abstract for you guys, but you want to make sure that like your total harmonic distortion is extremely low so that you're not frying integrated circuits inside of all of your sensitive electronics. So.
I thought it was like, give like 3 separate.
What do you mean by put them all together and put that in?
3 wires, right?
Mhm. If you just tried to tie those 3 wires together,
Yeah.
you're probably gonna start a hell of a fire.
That's what happened.
So effectively,
3 separate voltages, put 3 voltages together in.
so here's the deal. All right, so you're kind of glossing over some quite important facts, okay? So what is a voltage? It is a difference in electric potential between 2 points. So if you were to connect those 3 points together from an ideal circuit scenario, you're literally breaking physics, because all of those voltage drops would have to somehow magically transform into 0 from whatever they were. In a real case, you're forgetting about the fact that wires have impedance. So voltage drops are going to occur over those wires. If you had a very, very large voltage drop over a very, very short section of wire, it's going to be passing a huge amount of current, which is going to melt the insulation, cause shorts, literally break the system down. That's why I say you're going to start a fire. Your cables are literally going to overheat trying to balance all of that kind of stuff out. Yeah.
It's not like it's like each of the wires had both the elements between being a source and the ground. If I'm understanding that correctly. I mean, it's like.
So in the time domain, what we would be seeing, so if we had a current flowing down the line in one direction, our return path would be the exact same current flowing down the line in the opposite direction. So what you would really see is 2 sinusoidal currents that are exactly 180 degrees out of phase because they are in opposite directions. So they're both going to be sinusoidally varying, but there's a phase difference between them. So one of them isn't really behaving like ground. We don't have to have a ground in an AC system. We usually do tie things back to an earth ground and all of that kind of stuff. But in an AC system that contains a single phase AC system that contains a hot wire and a neutral wire, the neutral wire is what we commonly associate with the negative polarity terminal of all of our voltages. But all an AC voltage means is that the potential between those two wires is constantly changing in time. Doesn't matter what the individual potential on either of those wires is, we just know that the difference between them is exactly some amount.
Got like, they're varying in when they're positive or negative.
Mm-hmm.
One of the wires at one time could send in all the power forward. So all the electrons traveling towards the load. Whereas the other two wires, like, since they're kind of stable, the other wire would be slightly slower because it's sending less power. Still have something back through.
It is indeed why electrical engineers get paid the big bucks. All right, so let's talk about power distribution and all that kind of stuff. So we touched on this a little bit on Tuesday. So let's say this is a simple system, right? So we have a power plant. Then we have here, I'm just going to call this transmission network. This is usually just a set of wires. We will typically wind up having to step that back down to something smaller. Sorry, I drew that. So here would be our distribution network. And then another transformer. And then way over on this side, would be our home or a small, what's called usually a secondary customer, which would be a residential or commercial consumer of power. Okay. So everything to the left of this line is typically referred to as generation, right? So we're talking about stuff in the ballpark of 20 kilovolts RMS, at least around here. from the secondary of that first power transformer all the way up to the primary of the next power transformer, we are in the transmission regime. So this might be 345 kilovolts RMS. Then we hit our substation, which is what this next transformer is really representing. And then we're on the distribution side of things. And the connection to our home is also falls under the umbrella of distribution from the electric utilities standpoint. So over here on this side of things, we're typically looking at voltages in the ballpark of 13.8 kilovolts RMS. And then when we're down to a home consumer, we're looking at 240 volts RMS for a single family home. And it's usually 208 volts RMS if you're looking at an apartment building or something like that. So let's talk about why that's kind of different. Okay. So a single family home is provided with a single phase of power from an electric utility. Okay. So we are just getting effective one phase, but if we're talking about a larger apartment complex, it's usually supplied, or a building like the ISB here in Efkin Hall, it's supplied with three-phase power. So in order for us to get 120 volts in our homes from these receptacles, we utilize what's called a tapped or split phase transformer. So it's going to be something like this. So here we have our primary side. And since we're only dealing with magnitudes, the dots don't particularly matter, so I'm not even going to bother drawing them. But this voltage right here would be 13.8 kilovolts RMS in magnitude. And then on this side of things, we would have something like this. Give myself enough room. So this secondary winding of this transformer would be what we call tapped. And all that is inserting an extra conductor halfway through the windings of our coil, so that, actually, let me move this one back a smidge. So that the potential difference between here and here is 240 volts RMS. And then typically we would have 120 volts between here and here. And 120 volts between here and here. And we get the exact same magnitude, but effectively those voltages are of opposite signs. So in your home, connected to your circuit breaker, you have access to either 240 volts, positive 120 volts, or negative 120 volts. But there is literally no discernible difference between the positive 120 volts and the negative 120 volts, because the overwhelming majority of simple loads don't care about that 180-degree phase shift, right? It is. So the split is located, it's on the transformer, but it's also physically in your circuit breaker panel. So let me do a quick Google here. Let's see. Load center. Images. see if we can find one.
Like,
Yeah, so the neutral bus is effectively this guy right here, and then we have a hot on either side that's giving us the 240. And if we measure from hot to hot, we get the 240. So if we look at, wish there was a better thing here. I'm trying to see if there's a bigger picture here, or a better picture here, but effectively our breakers just clip in. And on one side, they're effectively on the positive 120 side, and on the other side, they're the negative 120 side. And actually, that's not true. It's going to go positive 120, negative 120, up and down. It's kind of like a laddered structure based on those little tabs and all of that kind of stuff. And so if you ever see a breaker that actually takes up two spaces, that's for a 240 volt circuit.
Oh,
That's literally all it is. Back in the day, you very much not up to code anymore, but my mom's house is crazy old. So you would see like old school breakers would have a hole through the switch where you could literally put a pin in it to tie two breakers together, so that you could use two 120 volt breakers as a 240 volt breakers, because if one of them tripped, it would force both of them to trip. They don't do that anymore. It's super illegal.
yeah, they can still.
Why would you want 240 volts? So your dryer, your electric range, all of those are 240 volt. Usually a washing, actually not a washing machine, a hot water heater, 240 volts. Things like lights and all of that kind of stuff, small appliances, so your microwaves, all that kind of jazz, are 120 volt appliances. What's kind of interesting is this is just how we do it here in the United States. In Europe, everywhere just gets 230. Doesn't matter what the load is, it's just 230. So they don't do this split phase power at all.
Here's better. Curious to see if you have an opinion.
Okay.
I guess that break box is typical for North
Mhm.
America. The North American breaker box compared to, let's say, like the European one, the Siemens switches.
Mhm.
Do you think which one, do you have an opinion of which one actually better? Because
I
I know they're set up slightly different on internet.
I am of the opinion that the split phase systems that are used here in the United States are arguably a little bit safer. Because 120 volts is less of a shock than 230 volts. That's pretty much it. It's still going to hurt either way, but 120 is slightly less painful to get hit by. So I personally think the American system is a touch safer, but it's not really that big of a thing. Because we're comparing 240 volts to 230 volts, or 240 volts at 60 hertz to 230 volts at 50 hertz. That's the maximum amount of potential that you can see in a residence. So they're realistically extremely similar, but most people only have a couple or a handful of 240 volt outlets in their home, specifically for larger appliances, right? So most people are only going to interact with the 120 volt receptacles regularly. So there's a slightly less danger of shock from those. So anyway.
So sure, all their plans. They want to have a little.
To do what? They're all designed to use 230. So that actually is circling back around to what I was going to talk about. So we're talking about this kind of stuff for a residence here in the US, where we're looking at a single family home where appliances are designed for either 240 volts or 120 volts. But I talked a little while ago about how in an apartment complex, you might not have 240 volts because instead the apartment complex is fed through a three-phase system. So their access is going to be either between the A and B phases where they would have 208 or the A and neutral phase where they would have 120 of their transformer. So they have 120 for smaller loads and then 208 for their water heaters, ovens and all of that kind of stuff. So actually most appliances here in the United States have to be designed to work for both 240 and 208 so that you don't have to have special appliances for large scale apartment complexes and all of that kind of stuff. What does that mean realistically? Well, your oven's going to get slightly less current to it, which means it's going to take a little bit longer for it to heat up. Yeah. So it's going to try to draw as much as it can based on the system that it's connected to. HVAC units, similar kind of thing. The compressor is going to run a little bit differently because it's getting 208 versus 240, but in the grand scheme of things, it doesn't make that huge of a difference. So different regions of the world design their electronics slightly differently because they have to worry about changes in frequency. And so here in the US, we use 60 hertz. There are other countries that use 60 hertz. I think Australia does, but I'm not 100% sure on that. Most of Europe uses 50 hertz. So there are lots of little considerations. So you guys have, most of you have interacted with at least a desktop computer, right? Yeah, so most of you guys have interacted with a desktop computer. That desktop computer's power supply, if you look at the little sticker on it, it's actually rated for several different voltage and currents. And so you can just change out the cable depending on where you want to install that particular computer. So like if we look, this is kind of a tangent, but it's related. No, this is all related to what I'm trying to talk about. We're done with the math for whatever, you know. Yeah.
Well, I also know that like I've heard some people say like when you go to Europe and stuff, you have to be very mindful of like your phone or power supply.
Yeah.
It's like if you are not mindful of that.
Most chargers for laptop or cell phone, if you read the fine print, they're rated for 100 to 240 volts, AC, 50 to 60 hertz.
Yep.
So they'll work in Europe, but you need an adapter because the plug configuration is different.
So that is exactly what I was.
Voltage is just.
Yeah. Yeah. So
It's like, oh yeah.
But all standard adapters these days will work there.
Yeah.
If anybody's only charger just to make sure, yeah, that's,
Yeah.
and you still need to buy physical adapter.
So like this C19, this is a particular socket that's used for most computer power supplies, but the cables that you can get for that terminate in like NEMA, I guess it would be, I think like 5P15. So effectively it's rated for 15 amps, or you can get them rated for 20 amps here in the States. Or they might be, so this guy over here is like a C19 setup, but effectively it's just literally changing the plug-in. Some power supplies and all of that kind of stuff. So like if you buy, if you're a nerd like me and you're interested in guitar amps, Marshall amplifiers, probably one of the most well-known guitar amplifier manufacturers in the world, is based out of the UK. So all of their heads, their amplifier heads, have a switch on the back that you effectively switch if you want it to be configured for American or North American power or European power, and it literally is just using a different plug. So you switch things over so that the tubes are biased correctly for that particular place, and then you connect the right plug to the outlet that you have. Most modern electronics are designed to be used in a global marketplace. So anyway. All right, so what I want us to do now, I said we were done with the math, but I lied because I forgot I wanted us to work a very simple problem. Okay, so let's say that we have a situation like this, right? Where we have our 13.8 kilovolts nominally across the primary terminals of our pole pig transformer, where that's just the common name for most of the transformers that you see attached to utility poles in residential areas. And then over here on the secondary side, this is connected to a home. So here you would have positive 120. And here you would have negative 120. So that we have 240 total. And between, so on one side of this thing, we have a lighting load. So this would represent, I don't know, the number of lights I have on while I'm cooking dinner. So this might be 8 times 100-watt bulbs. I think there's in the ballpark 6 or 8 light bulbs in my kitchen area. Okay. My wife might be in the living room watching TV. It might be connected to the other 120 volts. And then if I'm cooking dinner, I'm probably using my stovetop. So this is the oven. Let's say that the oven is drawing 5 kilowatts and the TV is drawing 350 watts. What I want us to figure out is the current, the magnitude of the current that's flowing in the transformer. So how much current effectively am I drawing from the electric utilities perspective of things? So anybody have any thoughts on how we might approach a problem like this? So what's the total power that I'm drawing while I'm cooking dinner and my wife's watching TV? So I think it's going to be the 5 kilowatts from my oven, the 350 from my stove, excuse me, from my television, and the 800 from my lights. So I'm just going to add these together. So 5,000 plus 350 plus 800 would be 6,150 watts. Oh. Yeah. Yeah, so if everything that we're talking about is a simple resistive load and everything that I have mentioned here would be pretty much a purely resistive load, then Sam, you're absolutely correct. The current on our secondary side would simply be P total divided by 240 volts RMS. So 6150 over 240 would look like 25.625 amps RMS. So it looks like when I'm cooking dinner, I'm actually drawing about 1/4 of the total amount of current that I can have in my home at any given time because I have a 100 amp service connection because I don't have a huge house. So what's that current going to look like on the primary side? So what's the current flowing through the primary windings of the transformer? It is. We could do that, sure. So we could do 13.8 kilovolt, excuse me, 6,150 watts divided by 13.8 kilovolts. That'll give us, so 13.8 kilovolts RMS, 6,150 watts. Zero point 446 amps RMS. What if we used our transformer relationship? What do you think would happen? What's our turns ratio? So it'll be the other way around because we've considered our turns ratio to be the number of turns on the secondary divided by the number of turns on the primary. So 240 divided by 13,800 is 2 over 115, right? So if we multiply that 25.625 times 2 over 115, we get literally the exact same number, which we would expect. What I'm saying is if we know the current flowing in our house, we can just use the transformer's turns ratio to figure out what's going on external to our house and all of that kind of stuff as well. There's always going to be 2 or 3 different ways to solve for these things. Now that we know how transformers work, we can use those relationships too. All right, I think that's enough out of me. We've talked about 3-phase transformers. We've introduced a little bit of the concepts of generation, transmission, distribution, and all of that kind of jazz, so that when you guys go off to internships and all that kind of stuff, you at least have some idea what the hell people are talking about. We'll work on more of the practical details in 360. So I'm done with this class. Now it's time for talking about the test. So my plans for the test, first, a few people asked me if it would be possible to take their exam on Thursday next week. I am going to allow you all to choose whether you take your exam on Tuesday or Thursday. You do not need to send me an email or anything like that. Just whichever day you show up on is the day that you're taking the test, and we're good. I've got time on both Tuesday and Thursday morning. I want to make you guys aware that, I hope it's kind of obvious, there will be two different tests because I don't want people that take the test on Tuesday to go tell the people that take their test on Thursday what's what. So anyway, you have the option of taking your exam, your final exam on Tuesday or Thursday of next week. So whatever works with your schedule is totally fine by me. As far as the material on the exam goes, so I'm expecting to give you guys, so one problem based on, let's see, we're at homework number 10 right now. So I think one problem from homework 8 type stuff. So that would be involving you guys writing the equations out for a system that has magnetically coupled inductors. I'm not gonna make you solve it or anything like that because that would require a tutor. So it's gonna be one of the grosser ones that we haven't learned other tips and tricks to be able to do by hand. Okay. So one problem akin to homework number 8. One problem akin to homework number 9, where we could use things like transformer equivalent circuits, input impedance method, and all of that kind of stuff to actually be able to solve things by hand. So that would be one problem from the magnetic circuits, one problem from, I guess we call it practical transformers, and then there will be 2 problems related to ideal transformers, which are the material that we've been covering Tuesday and a little bit today. Not going to ask you anything about a 3-phase transformer, by the way. Just want to be clear about that. So 2 problems that will be similar in nature to what we saw in homework set number 10. Dealing with ideal transformers. Yeah, and I may be misremembering the homework numbers, but effectively the material from the last test. So the first lecture, 1 problem, the second lecture, 1 problem, these last couple of lectures, 2 problems. It'll be subdivided into 10 total parts. So, you know, asking questions about what's the input impedance, like I do on the homework problem. So if we look at the homework problem, just trying to not get too distracted here. This would probably be the easier way to describe what I'm talking about anyway. No, I don't want to change the text. I want to open the damn file. Open the folder. Jesus. I have indeed. I even got my mouse out and it's just like, nope, I'm going to be a jerk about it. Let me look at things here really quickly. Oh, I'm getting pissed off. Yeah. Sorry, I must have misspoken. So homework 9 was the one with magnetically coupled circuits. So something kind of like this problem right here, or like the in-class assignment related problems where we just have magnetically coupled coils, and I'm going to give you specific directions for your currents. I'm going to give you specific polarities for your voltages, and I'm expecting you to be able to write the system of equations that you would need to solve it, kind of like we did on exam 1 with the mesh and nodal thing. So something akin to that will be one problem. A problem like this one right here, to where we could use either a transformer equivalent circuit or the concept of input impedance in order to solve for the quantity V out. So something like that is also fair game. And then when we look at homework number 10, which this one opened without issue. Something like problem 3 and or problem 4. So problem 3, we have an ideal transformer. I'm asking you to do some, what I feel are simple calculations on primary and secondary voltages and currents. Problem 4 is a similar thing, except that you have to use the Thevenin equivalent circuit because there's a voltage source on both sides in order to make things out. So you're either going to have to refer everything from the secondary over to the primary, or everything from the primary over to the secondary in order to simplify the circuit enough to do analysis. So those are my expectations for this upcoming test. So if you're doing these homeworks and you've studied the in-class assignments and all that kind of stuff, you will be as prepared like every other test I give you. Yes. Mm-hmm. disagree. You should be flipping the impedance every time. So if you reflect the impedance over from the secondary to the primary or vice versa, you're eliminating the transformer's existence in the circuit at all. Because you're just saying effectively, these terminals over here see this, now I don't have to worry about transformer relationships. I just have a simple single loop circuit in the frequency domain that we can analyze. So how I worked all of these problems when I was coming up with their solutions. So just for the sake of argument here, if we're looking at problem 3, I took my secondary loop impedance of 100 minus J 75 ohms, reflected it over to the primary side so that it would look like, what's 100 divided by 25? That would be 4 minus J3. And so I have 12 angle 0 in series with 2 plus J3 in series with 4 minus J3. V1 is just the voltage drop over the 4 minus J3 ohm impedance. I1 is just the current flowing through the 4 minus J3 ohm impedance. And then I use my transformer relationships to figure out V2 and I2. So I reflected everything from the secondary over to the primary, analyzed it as a just single phase AC circuit, and then use transformer relationships to figure out what was going on in the secondary. For problem 4, very similar thing, except not only did I reflect that impedance of 100 minus J60, I also reflected that voltage of 10 angle 30. So when we reflect the impedance, we divide by A squared. When we reflect that voltage source, we just divide by A, based on our definition of the turns ratio N2 over N1. Once we have it as, once we move that voltage source and that 100 minus J60 ohm impedance over to the other side, we just have a simple circuit with no transformer in it whatsoever that we can analyze very easily. Yep, just impedances and voltages, absolutely right. So to reiterate, I personally am of the opinion you should always reflect them, usually over to the primary side. That being said, for this one in particular, where we have a voltage source on either side, we could just as easily reflect everything that's connected on the primary over to the secondary, do our analysis, and we'll wind up with the exact same results, except that we'll find the secondary side things first, and then use the transformer relationships to find the primary side quantity. Excuse me. So, I will, like I said, 10 total parts, just like the last test. I will be available for office hours for this week, and next week and all of that kind of good stuff as well. If you have any questions about stuff. So yeah, that's what I've got.